We're going to wait a couple of minutes so that everyone can join us. Typically, people take a few minutes to start filtering in. So I suppose while we wait on that, let's go ahead and get a warm-up. How about it? Good evening. Hope everyone's doing well this evening. I'm having dinner from the porch delivered at 8 p.m. So I'd say I'm doing pretty well. That's a good restaurant. It's one of my favorites. Winston has a lot of great food. So as we're filtering in, so because it's going to take everyone a few minutes to join us, as we come in, let's just work on this warm-up problem. Let's just take a minute to go ahead and work on this. It'll probably take most of us not that long to complete, I imagine. Certainly hope more people in this will join us. We have more people in this registered for our class, I think. Let me double check. Oh yeah, we have 18 people. I'm in the right place at the right time, right? Man, whenever people don't show up, I start to get concerned. Like, did I scare everyone off yesterday? Was it that bad? I haven't seen any drop forms come in, so. Hey, let me go ahead and show everyone also. So since we've been working on this for a minute, I think I need to not keep my phone on my digital acoustic converter because I have an iPhone and I think the magnet causes some interference in my headphones. So let me show us all how to access the recordings real quick. As some of us haven't used Collaborate before, I have to kill that. Then I have to share. I hope this is it. Yep. So this is where you came to access the class, right? You clicked on this. Instead of clicking on this, if you want to access the recordings, click right here on these 3 lines. That's a menu button. And then click on recordings. And the recordings will show up here. They take some amount of time to process. Does that make sense? How to access the recordings? Again, you just, up here where it says sessions, top left, click on menu, click on recordings, boom. Easiest thing I've ever done, actually. So if you're unable to make it to a class for some reason, everything is going to be recorded. And if our class is not yet being recorded, like I know it's not yet because I'm just running through how to access the recording, and how to access the recording would be pointless on a recording. Please let me know if I start lecturing and I have not yet begun to record. So let me go ahead and share Microsoft OneNote again. I have a decent number of people now. I don't know why it was saying that my connection wasn't great there. I have gigabit. My connection should be phenomenal. There should be no delay. Let me just hit up fast.com real quick in case AT&T is gigabit. It's the fastest internet that you can get, like in the world. Yeah, it says I have 750 megabits per second. I sometimes stream on Twitch for fun. No one ever watches, but I do it for fun. Anyway, let's get started. And no, none of you will ever figure out my username. I'm not an affiliate. Today we're going to talk about sections 1.3 through 1.5. Oh yeah, did we solve the warm-up? This one's easy. What's the slope here? Yep, it's just we plug in 200 here, right? For D. And our slope is going to be whatever 200 times 0.0417 is. Which is 8.34, that's correct. What does the slope represent? What does the slope represent here? The number of milligrams that should be administered to a person per year of their life. Yeah, that's correct. Good job. Good job in remembering the year part here because slope is a rate. And what is the dosage for a newborn? (8.34 milligrams. That is also correct. Perfect. That's what we get if we plug 0 into this, right? A newborn is 0 years old. Although I suppose that depends on your perception, right? In some cultures, you are considered to be a year old by the time you're born. That's why, like in South Korea, for instance, there's a different age reckoning system, right? Yeah, like my buddy Minsong says that he is, well, I guess he'll say now that he's 30, right? But I'm older than Minsong. But Minsong is 30 years old in Korean age, despite being 29 years old in what they call international age. It's pretty interesting. I like learning about different cultures. So let's talk about section 1.3 here. 1.3 is largely about transformations of functions. It's how we can obtain new functions from old functions. I went ahead and I condensed a bunch of stuff into one page for us, so we don't have to go through two separate pages of back and forth here. The basic idea here is if I add or subtract a number from a function, it's going to move the function in some way. So here, we'll just look at vertical and horizontal shifts first. I want to make this a little larger. If I add a number that is greater than 0, we're letting this arbitrary number c be greater than 0. If I add c to the outside of a function, we shift the graph up c units. If I subtract c from the outside of the function, we shift the graph down c units. If I subtract c on the inside of the function, that is, if I replace the x in the function with x minus c, then this shifts the graph to the right by c units. And if instead I replace that x with x plus c, this is going to shift the graph to the left c units. Does this make sense? I think that we've seen this before, right? This is just a refresher. These first few sections are just to, jog our memory, essentially. We've probably seen this, but it's always good to see it again, right? This is the first slide. Yeah, this is all the first slide. And here we just have some graphs just to visually, show you how these things compare to one another. This is just some arbitrarily defined function. It doesn't matter what the function is. Another way that we can find or obtain new functions from old functions is through vertical and horizontal stretching and reflecting. Again, assuming that c is some number, this time greater than 1. If I want the graph of c times x, I stretch the graph vertically by a factor of c. You can see the effect of that on this right set of graphs above this box, right? You can see f of x compared to c times f of x. That is assuming that c is greater than 1 here. If instead you multiply f of x by 1 over c, you shrink the graph of f of x vertically by a factor of c. This is why it's important that in this red graph that c is greater than 1. Because for this green graph, 1 over c ends up being between 0 and 1. If you replace x with c times x, that one is not graphed here, is it? That one's not graphed here. That shrinks the graph horizontally by a factor of c. If you, okay, you're just responding to the question. If you instead replace x with x divided by c, we stretch the graph of f of x horizontally by a factor of c. So notice that the vertical and horizontal stretches, they behave opposite of one another, right? That is in regards to shrink versus stretch, right? Do you see what I'm talking about here? Just multiplying by c here and multiplying by c on the inside is different. Yeah, okay. Wanted to call attention to this. It's easy to get this mixed up and think, oh, well, it's a stretch if I multiply by c on the outside, so it's a stretch if I multiply by c on the inside, right? When in fact it's a shrink if you multiply it by c on the inside. It's a horizontal shrink. If you put a negative sign on the outside of the function, this operation is equivalent to changing every sign in the function. So if you have a polynomial, this means that you're changing every single sign of that function. This is a reflection of the graph about the x-axis. So you see down here this orange, yellowish, it's probably more orangish graph is reflected across the x-axis. And if we replace x with negative x, this causes the graph of y equals f of x to be reflected across the y-axis. So these two reflections, right, we saw these yesterday when we discussed odd and even functions. Specifically, do you remember that, so f of negative x equals f of positive x, this makes something even, right? This means that a reflection across the y-axis doesn't do anything to this function. Does that make sense? And similarly, f of negative x is equal to negative f of x. This means that the function is odd, right? And that means that these two transformations are the same for odd functions. For odd functions, a reflection across the x-axis is the same as a reflection across the y-axis. It ends up giving us the same graph. Does that make sense? And you can experiment with this in Desmos and see this. I think this stuff is pretty cool. Oh, sorry for the dog. That's Dr. Doom. Do we have this? Can I flip over to the next page? Can I scroll up? Yeah. Do you need this box up here? Will we have time for homework questions? We might have time for homework questions. We'll see at the end of class. Let me turn the brightness down on my monitor a little bit here. I'm looking at these monitors for a long time every day, so. Oh, 1 second. I need to figure out how to turn the brightness down on my rightmost monitor. I'm not super familiar with the controls in this one. There it is. There's the menu button. Up. Brightness. Okay. All right, that's pretty good. There we go. My eyes were starting to hurt a little bit there. Too much light beaming into my eyes. Let's look at some examples. The graph of y equals f of x is given. Match each graph or match each equation with its graph. Do you see that these are numbered over here? It might be a little hard to see here, but these are numbered. This is 1, 3, this one's 4, this one's 5, and this one's 2. Does that help? Okay, so match each of these equations with its graph. And by that, I mean you. What I'm going to do is I'm going to throw up a polling question that says, I am done with the question. I have completed the question. I finished answering the question. And once you're done, you can click yes. I'll give us just a minute to do this. All right, a few of us have finished already. Oh, by the way, if I ask you to complete a question, you can you're totally allowed to like talk to each other. Like you can chat with each other in the chat box to help each other work out the question, or you can turn your mics on. That's totally cool with me. Collaboration is cool. I encourage it. This class is going to be a little bit less boring if we work together, right? Not that I think calculus is boring, but maybe to some of you it is. So a lot of us are finished now. All right. So what do we get for A? Three. Do we agree with 3? Okay. I think 3 is our consensus. What do we get for B? 1. Okay. What do we get for C?
4.
4. All right. What about D? 5. We agree with 5. All right. And then by process of elimination, I hope that we got 2 for E. Right. There's nothing else that it could be. Let's see. You all passed. Good job. 100%. Good job. Did we do number 2? Did we create the function? Okay, so you replaced the... Yep. So those are the transformations that you would apply to get from this left function to this right function. Yeah. So that's correct. We want to notice that we have a vertical stretch by a factor of 2 from the left graph to the right graph, right? Because previously in the left graph, our highest y value was 1.5. In our right graph, our highest y value is 3. For some reason, it says that can you guys still see this? Blackboard wants me to reload the session for some reason. I guess I'm going to do that real quick. It says that my connection isn't good enough, but it should be. Maybe I just click X on that. That's fine. Should we include the old function in the new translation? It depends on what you mean by that, I suppose. Since the old function is f of x, 2 times f of x minus 2, which, the x minus 2 portion is from shifting this to the right 2 units. Previously, it started at an x value of 0. Now it starts at an x value of 2. You do need that, right? Because f of x is 3x minus x squared. So 2 times f of x minus 2 is 2 times the square root of x minus, or let's see, 3 times x minus 2 minus x minus 2 squared, right? Is that what you were asking? Yeah. Yep. This is exactly, this is what we want here. And we could multiply this out and simplify it a little bit. I think it's actually probably fine like this. What do you think? I don't see an issue with keeping it like this. So let's move on to the next topic. We're still in 1.3. Boop, 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 boop. The next topic is ways in which we can combine functions. This is still in 1.3 because 1.3 is all about obtaining new functions from old functions. If I have two functions, f and g, I can find the sum, difference, product, and quotients of those functions, right? No big deal. These are written as f plus g of x, which is equal to f of x plus g of x. F minus g of x is equal to f of x minus g of x. F times g of x is f of x times g of x, and f divided by g of x is equal to f of x divided by g of x. The left-hand sides are just kind of some notation that is sometimes used as like a shorthand. So very important to this is we need to discuss the domain of these kinds of combinations of functions. If I add two functions, for instance, what is the domain of the resulting function going to be? Not necessarily, right? Sometimes functions have restrictions on them, right? Sometimes functions have some restrictions on their domains. Like the square root function, you can't plug anything negative into a square root, right? Let's say just arbitrarily, let's say A is the domain of F. Let's say that B is the domain of G. The domain of F plus G is this. Does anyone know what this symbol in the middle of A and B represents? Union is like this. So this one isn't a union. This is an intersection. The intersection of A and B. We could read this as A intersect B. So this symbol in the middle of these two symbolizes an intersection. And what is meant by an intersection is everything that is in A and B. Everything that is in both of them. It's the intersection of these two sets, yes. Everything contained in both of them. For instance, let's do a little bit of, elementary set theory here. Let's say A, yes, question. Question, Jordan? Let's say A is the set 0, 1, 2, 3, 4, and B is the set 1, 4, 7, 8. The intersection of A and B is going to be everything that is contained in both of them. It's going to be all of the overlap. So what numbers are in both of them? 1 and 4. So A intersect B here is the set 1, 4. Does that make sense? Just so we can understand what it means here by an intersection. And maybe just so we can get a better idea of what a union is. A union B is going to be just everything from both of them thrown together. So this is going to be 0, 1, 2, 3, 4, 7, 8. Right. We don't have to write the 1s and the 4s twice because they're already taken care of just by writing it once. Does this make sense? This is what is meant by union and intersection. I don't know if this was ever explained to you before, or if, someone just started using these words. So the point here is the domain of f plus g is A intersect B. What do we think the domain of f minus g is? And these were just arbitrarily defined here, right? A and B aren't necessarily those sets, right? I just arbitrarily defined some numbers. I made something up. If A is the domain of f and G is the domain, or B is the domain of G, what's the domain of f minus G? This one seems tricky, but it's also A intersect B. For instance, let's look at a case where, let's say f of x is the square root of x. And let's say g of x is the square root of 2 minus x. What's the domain of A? Or what's the domain of f of x? What is A? What numbers can I plug in for x? Anything larger than 0? What about 0 itself? I'm allowed to take the square root of 0. So anything greater than or equal to 0 is the domain of the square root function. I'm allowed to take the square root of 0. You can go ahead and do it in your calculator, even. What about for g here? What's the domain of g? Yep, anything greater than or equal to 2. So the domain of f plus g of x, which is the function square root of x plus square root of 2 minus x, is the intersection of, oh wait, no, hold on. We made a mistake, didn't we? If I plug in something greater than 2 here, if I plug in something like 3, what do I get? We made a mistake. I almost didn't catch it. This is going to be anything less than or equal to 2. Do we agree? There we go. So this goes from negative infinity to positive 2. If I plug in something greater than 2, for instance, if I try plugging in 3, then I'm taking the square root of a negative number. So I have these two domains here, 0 to infinity and negative infinity 2. And the domain of this sum of these functions has to be the intersection of the two respective domains. So what is contained by both of these? What's the smallest thing? What's the smallest number contained by both of these domains? 0. Is 0 going to be included or is it going to be excluded? It's going to be included, right? So 0. What's the largest number included by both domains? 2. Is 2 going to be included or excluded? Included. Very good. So this is the domain of f plus g of x. Does this make sense? Can I explain again why? So why what? So the intersection of these two domains is the stuff that's contained in both of them, right? It's all the overlap of the two domains. So the smallest number that's in both of them is 0, and the largest number that's in both of them is 2. And those are both included. And this is because, yes, in fact, whenever multiplying as well, we're about to discuss, whenever multiplying two functions, the resulting domain is also the intersection of the domains of f and g. Yeah. And it's because both functions need to be defined, right? If we allowed the domain to be something that was not the in the intersection of these two domains, then we are allowing for one of the functions to not be defined at a certain point. Does that make sense? Cool. You know, I think that this is the toughest part about calculus, is we have to get through all this review. Now, once again, the domain of, like I just said, the domain of f times g of x is also A intersect B. In fact, the domain of f divided by g of x is, what do you think this one is? What do you think this domain is? This one's a little trickier, huh? G can be less than 0 also, right? You're allowed to divide by negative numbers. It's the intersection of A and B except the places where G is 0. So the way we can denote this is x is an element of A intersect B such that g of x is not 0. Nope, not the number e. Element symbol. And this bar stands for such that. X. So we can read this as x is an element of A intersect B such that g of x is not 0. What is 0 is not in the domain of g already. It doesn't matter if 0 is in the domain of g of x necessarily, because g of x can be equal to 0 sometimes, depending on the function. It matters if 0 is in the range of g. If 0 is not in the range of g, though, then it's a non-issue. Like if we have a, for instance, if we have an exponential function that's not shifted, right? Exponential functions are never equal to 0, right? So dividing by an exponential function will never cause any issues with our domain. Does that make sense? Such that, so whenever we say g of x can't be 0, we mean the outputs of g of x can't be 0. Does that make sense? For instance, let's say f of x is I don't know, the square root of 2 minus x, like we just had. And let's say g of x is I don't know, x squared minus 4. Or here, x squared minus 1. I like that better. F over g of x is the square root of 2 minus x over x squared minus 1. I need to find the domain of this function. This is going to be the intersection of these two functions, except where my denominator is equal to 0. So what's the intersection of these two functions? Well, I can start by asking, what's the domain of g of x? What's b? What numbers can I plug into this function? We already said that the domain of this one is this. What's the domain of g of x? Well, the domain of g of x is everything, right? I can plug any number into g of x. I'm allowed to get 0 out of a function. So if we found just A union B, then you see A union B would just be the same thing as A in this case. Do we agree? So what we're saying is the domain here is A union B except the places where g of x is 0. So this is going to be negative infinity to 2 except, and we're not going to write the domain like this. We're going to come back and change this in a second. Once we find out where g of x is equal to 0. Except where x squared minus 1 is equal to 0. So I can solve for x here, right? Add 1 to both sides. X squared is 1. Take a square root. X is plus or minus 1. So plus or minus 1 have to be excluded from my domain. So the domain of this function is negative infinity until the first number that causes an issue with the domain, which is negative 1. Union, starting back with that number that caused an issue, continuing until we get to another problem, a positive one, union 1 to 2. Does that make sense? This is all the places, this is the union of these two domains, or the intersection of these two domains, except for the places where g of x is equal to 0. Does that make sense? We're not including -1 and +1. We're only including the stuff in between them. That's why we have the parentheses here. We have to include the stuff in between -1 and +1, right? For instance, I'm allowed to plug 0 in here. 0 doesn't cause any issues, right? Does that make sense? Yeah, in the graph of this function, there are going to be vertical asymptotes at x equals plus or minus 1. There are going to be vertical asymptotes there on this graph. Or some people like to call them infinite discontinuities or non-removable discontinuities. Does that make sense? Let's go on to our next thing here. Our next thing is just on compositions of functions. If we have two functions, f and g, the composite function, f of g, also called the composition of f and g, is defined by the composition of f and g of x is equal to f of g of x. And I stole an image right out of the textbook. That's kind of a funny looking, kind of a weird picture, but I like it. This is a composite function machine. Remember that function machine image we had previously? This is that, but with composite functions. X is the input to G. G spits out some output, which is then the input to F. And our final output is F of G of X. Does that make sense? Yeah, question.
So that little circle in between F and G, that just means composition?
Yes, that's the composition operator.
Okay.
Yeah, good question. I think that thing has a name, but I don't know what it's called. Function composition, I don't know. I think I've seen someone call it a name before. I'm not going to spend too much time researching. Feel free to Google it and send me an email about it, though. So let's look at an example of function composition. Ring operator. Maybe. Yeah, I can go back. In fact, let me just take this with me. Probably the best thing to do here. I don't think it's a ring operator because rings are algebraic objects in modern algebra. Alrighty. Let's go ahead and look at this example together. Find the functions f of g and g of f. So f of g, all we want to do is take g of x and plug it in to f of x anywhere I see an x. Now that's a lot of x's that you just heard, but it is simpler than it seems, I promise. F of g of x, the way I like to write this is f of g of x is equal to, and I like to write out what g of x is next. G of x is 4x minus 3, right? So f of g of x is f of 4x minus 3. And this is what I get whenever I replace x with 4x minus 3 in f of x. And I can simplify that a little bit to be the square root of 4x minus 2. Does that make sense? Yeah, no problem. Can I go to the next one? The next, or g of f at least, is what I mean by the next one. Yeah, I don't mean the next page. Let's look at g of f. G of f of x is the same way, right? But this is g of f of x is square root of x plus 1. So g of square root of x plus 1 is 4 times square root of x plus 1 minus 3. Easiest thing I've ever done. Does this make sense? Now, let's think about how we can find the domain of this composition. We're talking about domain a lot. It's going to be important later, is why we're talking about it. And it's important now as well, but just know that us discussing it now doesn't mean it's it's unimportant later. It is very important later. I suppose before we discuss the domain of f of g of x, notice that f of g of x and g of f of x are not necessarily the same thing, are they? We got different results. These two functions are not the same, right? So keep that in mind. The domain of f of g of x is going to be the set of all x you know what? I'm going to skip that definition. It's going to get too confusing, I think, because I'm looking at it and I'm laughing. F of g of x is defined when both g of x and f of g of x are defined. What this means is I have to find the domain of f of g of x, and I also have to keep into I also have to take into account the domain of g of x, the inner function. I have to look at the domain of my composition, and I have to compare this also to the domain of my inner function. Does this make sense? Because if my inner function is not defined at a certain place in the domain of f of g of x, I have to exclude that place, right? Because my inner function needs to be defined for f of g of x to even exist. Okay. I really hope I'm making sense here. Sometimes I talk and I'm like, do I sound like a crazy person? So let's look at f of g of x. We said f of g of x is 4x minus 2, or square root of 4x minus 2, right? In our case here. So let's just find the domain of the square root of 4x minus 2. First of all. And then we're also going to have to keep into mind that g of x, our inner function, was 4x minus 3. We're going to have to look at the domain of that as well. You have to have g of x in order to find g of x has to be defined for f of g of x to be defined. Is what I'm saying. Yeah. So the domain of y equals 4x minus 3. By defined, I mean f of g of x is defined. I mean that a function value exists for this thing. So a function value of f of g of x can't exist if g of x does not have a function value at that x value. For instance, if g of x has a vertical asymptote at a certain x value, then I have to exclude that x value from f of g of x as well, because g of x is not defined there. Does that make sense? Yes, exactly. Does that make sense? It's because I have to make sure that all of my inputs from g of x are, I have to make sure that f of g of x is my inputs for f of x, or for f of g of x, right? So I can only have inputs that exist, essentially is what I'm saying. All right, let's continue here. The domain of the square root of 4x minus 2. This is anywhere 4x minus 2 is greater than or equal to 0. Right? We just have a little bit of algebra here. 4x is greater than or equal to 2. X is greater than or equal to 1/2. That's the domain of 4x minus 2. Or in other words, in interval notation, 1/2 to infinity. The domain of 4x minus 3 is all real numbers, right? It can be denoted with this fancy r. So I don't have anything in my g of x, in my inner function, that causes any issues, do I? I don't have any like divisions by 0 occurring here. I don't have any restrictions in this domain. So since I don't have any restrictions in the domain of g of x, I don't have to further restrict my domain of f of g of x. So this itself is the domain of f of g of x in this case. Does that make sense? Let's do a harder one. Let me see if I have one here. Let's see. This one isn't going to be affected either. Let me look at this one real quick. Okay, let's look at this one. If f of x is the square root of x and g of x is square root of 2 minus x, find g of f of x and its domain. Well, g of f of x is g of square root of x, which is square root of 2 minus square root of x. Interesting, huh? The domain of this by itself is going to be what? Anywhere 2 minus the square root of x is greater than or equal to 0. Right? So let's see, it's going to be anywhere. This is true, right? Squaring both sides, I get 4 is greater than or equal to x, which is the same as x is less than or equal to 4. Do we agree with this? What are we waiting at? I squared both sides here. Yeah. Not square root, squared. Yeah. Yeah. Because 4 is greater than x is the same thing as x is 4 greater than or equal to x is the same thing as x is less than or equal to 4. We can flip the inequality and flip the sign as well. In math, we very rarely have the variable on the right-hand side of the inequality is why. When do we flip the sign in other math stuff? If we multiply or divide both sides by a negative, then we have to change the direction of the inequality as well. Now, this is not all of my domain, though. This is not the only restriction on my domain. Because if I were to let x, so we said so far, x is less than or equal to 4 is our domain. But what if I plug -1 into this function? Well, that causes an issue, doesn't it? And that's because my inner function, which is f of x in this case, right? The domain of my inner function is causing a further restriction here. F of x is the square root of x. So the domain of this is x is greater than or equal to 0. I have to combine these two domains. I have to keep both of these restrictions in mind here. So the domain of f of g of x or rather, this is g of f of x, sorry, is actually x is between 0 and 4. This includes all the stuff that is greater than or equal to 0, that is less than or equal to 4. Does that make sense? Yes.
What happened to the large square root that went over square root 2 minus square root of x?
Where at? Like here?
Mm-hmm.
So the domain of a square root is anywhere that the argument, the stuff inside of it, is greater than or equal to 0. So I just said that the domain of this would be anywhere that its argument, which is this, is greater than or equal to 0.
Okay, because we were just looking for what x can be.
Yeah, I was just looking at what the domain could be. Yeah. It's the same way that we found the domain of the square root of 2 minus x. We take 2 minus x and set it greater than or equal to 0. Does that make sense? That's a generic way of finding the domain of a square root. Is I can just take the argument and set it greater than or equal to 0. Let's see. We worked out some examples. The last topic in 1.3 I want to talk about is this idea of decomposition of functions. We talked about composing functions. Now we need to talk about decomposing functions. The idea here is that I can express these two functions as I can express this one function as a composition of two functions. Oh, Ruth, did you have another question, or did I never lower your hand there? Oh, okay. So the idea here is that we just express this one function as a composition of two functions. And there can be multiple answers to this kind of problem. So I want to find, in essence, two functions, f of x and g of x, right, that I can compose to get this. What would you say the inner function is here? It might be easier to look at the inner function first. What could we say is an inner function here? Two x plus x squared? Yeah. Good. And then what's the outer function? X to the fourth? Yep, perfect. You guys are pros. Look at that. Easiest thing you've ever done, right? That's it. You solved the problem. Good job. Let's move on to 1.4. How about it? Let's talk about some exponential functions. Wait for what? Oh. You didn't need me. You just typed what it was. And then you could have composed them. Right? You didn't even need me. But of course, we don't often think of that kind of thing, right? I mean, that's just like we don't often think of the ways that we can like check our work, right? Like that's a way you can check your work. That's a Mr. Shields thing. It's a Shields thing. Megamind. I'm not Megamind. All right, I'm gonna move on. Is that all right? To exponential functions. These are our friends. Exponential functions are kind of cool, right? I'm certain that a lot of us have probably heard a lot about exponential functions in the past year, right? A lot of people have discussed COVID growth in terms of an exponential function. This is 1.4 now, yes. Right. You may have had a lot of classes that talked about, you may have had a math class even that talked about COVID growth in terms of an exponential function. I'm not sure. I haven't really wanted to use COVID as a math example, right? Because, man, it's all anyone's heard about for the last year, right? Yeah, I figure, and some of us have some people have lost loved ones and stuff like that, right? I don't want to keep bringing up that kind of stuff. So we're on the topic of exponential functions. I'll go back to that in a second, but we're not going to need the laws of the exponent laws yet. Whenever we talk about exponential functions, we talk about functions like f of x equals 2 to the x. This is an exponential function. Why is this called an exponential function? X is the exponent. Yeah. The variable is the exponent. This is what makes something an exponential function. Compared to f of x equals x squared, this is not an exponential function. A very common point of confusion is to think that this is an exponential function. What it is not. F of x equals x squared is a power function. It's strong. In general, let me grab my snipping tool. In general, an exponential function is a function of the form f of x equals b to the x. And this can take a few different forms. If f of x equals n, a positive integer, then b to the n is b times b times b, etc., n times, right? We also have a few other cases. If x is 0, then b to the 0th is 1. If x equals negative n, where n is a positive integer, then b to the negative n is equal to 1 over b to the n. If x is a rational number, p divided by q, where p and q are integers and q is positive, then this q in the denominator becomes the index of a root, and this p remains as an exponent here. Does this make sense? These are really exponent rules in disguise, right? And of course, we could play around with the graphs of these things. I encourage you to look at Desmos and graph these and play around with the graphs of exponential functions. This kind of brings us to, well, maybe I should show us some graphs. Let's look at a bunch of graphs. How about it? Can I move to the next page? Or are we still writing? Wait, okay. In addition to rewatching the lectures tomorrow, there are online tutor resources. We do offer tutoring through the tutoring center. I believe that they do both in person and online. Let me. Okay, I have a PDF that was distributed to me that can tell you how to make an appointment there. I believe that they also do drop-in in-person tutoring if that was something that you're interested in. Some people like to do it in person, so. Yeah, no problem. So if you're interested in that, you can send me an email, and I can just hit you up with a PDF. I have a PDF of how to register for it. I keep the PDF handy because obviously, since I haven't had to do it, like, since I'm not a student at Forsyth Tech, I haven't actually had to do the process myself, right? So let's look at a few of the graphs here. Let's look at some graphs of a few different exponential functions. This is a family of functions. We call these related functions families of functions because they're related. These are shown in this following figure for various values of this base b. By the way, this number, b, we call an exponential base. This number b, all of these numbers here, we call these exponential bases. We'll get used to this terminology eventually, if we're not yet used to it. Notice here that depending on the base, this graph changes a little bit, right? As this base gets large and positive, notice that this exponential function becomes more vertical, right? So as it gets smaller while remaining positive, this exponential function kind of flattens out a little bit, right? Notice that I have the graph of 1 to the x, I suppose just for reference. The graph of 1 to the x is just the graph y equals 0. I also have over here exponential functions who have fractional bases, right? I have this base of 1/2. I have this base of 1/4. Notice that as the denominator gets larger here, that these functions are also becoming more vertical, right? And you may also notice that almost, yeah, not quite the same. Although in this class, we are going to discuss how to find the instantaneous slope or the instantaneous rate of change of one of these functions. We're going to find that later on in this class. I'll be able to tell you, you'll be able to tell me the slope of one of these functions at any given point later on in this class. That's one of our end goals. So the idea here is look at this one and look at this one, right? Notice that this 1/4 to the x and this 4 to the x look oddly similar to one another. It looks like they might be mirrored, to me at least. And notice that 1/2 to the x and 2 to the x also seem to potentially be mirrored. We can break these exponential functions down into 3 different types of exponential function graphs, essentially. We have graphs where this base is between 0 and 1, We have graphs that are just 1 to the x. These ones are going to be unimportant because they're trivial and somewhat uninteresting, right, to discuss as an exponential function. And then we have these graphs of y equals b to the x, where b is a number that is greater than 1. These are these 3 types, essentially, of exponential function graphs. Does this make sense? Now, in order to discuss things like shifts of these graphs, we really need to know, or recall, I suppose, our exponent laws. These are just a few of them. Yeah. Cool. So these are just a few of our exponent laws here. If a and b are positive numbers and x and y are any real numbers, then b to the power of x plus y is equal to b to the x times b to the y. B to the power of x minus y is b to the x divided by b to the y. B to the power of x raised to the power of y is equal to b to the x times y. And a times b raised to the x power is a to the x times b to the x. These are some relatively basic exponent rules, right? If I'm adding the exponents, that's the same thing as multiplying these exponential bases, each with those respective exponents. If I'm subtracting these exponents, that's the same as division. If I raise an exponent to an exponent, I multiply the exponents. If I multiply 2 numbers and I raise that to an exponent, that's the same thing as raising each of those numbers to an exponent, that exponent, and then multiplying them. These properties are very, very important, and they're going to be very, very important in justifying the properties of logarithms whenever we get to those in just a minute, because logarithms are the inverses of exponential functions. They follow rules that are startlingly similar to exponent rules. Can I move on to the next thing? One thumbs up. Yes. I suppose maybe let's use some exponent rules real quick, just so we're familiar with them. Let's look at this as an example. Use the exponent rules to rewrite and simplify the expression. Maybe we'll only do A. Maybe we'll only do one of them. Let's look at A. So I have x to the 2n times x to the 3n divided by x to the n. Well, I think I can apply this first property, right? Because I have b to the x times b to the y. This is b to the x plus y. So x to the 2n times x to the 3n should be x to the 2n plus 3n, which is x to the 5n. Do we agree? Feel good about that? And now that I'm dividing these two, I have the same exponential base, right? I'm dividing two things that have the same exponential base. I can subtract their exponents. Is that okay? Let's look at B. We have enough time to do B. The first thing I want to do with B is I want to rewrite these roots as fractional exponents. Remember, we discussed that roots are fractional exponents. The square root is the same thing as raising something to the 1/2 power. And a cube root is the same thing as raising that number to the 1/3 power. Let's go ahead and distribute using this last exponent rule here up top. So that this is a to the 1/2 times b to the 1/2 over a, this is a, sorry. I need to find my eraser button. There we go. A to the 1/3. I can use my property that says if I divide two things with the same base, I can subtract their exponent. So this is a to the 1/3, 1/2 minus 1/3 rather, times b to the 1/2. 1/2 minus 1/3 is 1/6. So this is a to the 1/6 times b to the 1/2. Sorry. Does that make sense? Excellent. I'll give us just a second, and then we have to move on to 1.5. That's it for 1.4. We have to move on to 1.5, which will be our last topic for the night. Oh. Tomorrow, we're going to be covering 2.1, 2.2. Thursday, we're going to be covering 2.3. And then we would have done almost all of chapter 1 and 2 in this first week. All of chapter 1, most of chapter 2, or like half of chapter 2. That's pretty good, I'd say. What do you say? Let's move on to 1.5 here. It is a lot of content. It is a 7.5-week course, so we have to go fast, unfortunately. All right. The Monday, Wednesday meetings are indeed regular class. Yes. We're going to be going over new topics on those. If you cannot make it to those, there will be a recording. You can access the recording by clicking on the collaborate button, and then clicking on the 3 lines that are a menu button, and then clicking on recordings. Every class will be recorded. Except for this one, apparently, because I forgot. Oh, no. Oh, no. I'll start it here at least. Oh, no. I just saw the button that said, do you want to start? You recorded it? Upload that to YouTube. Upload that to YouTube for your... Wait, how did you record it? Oh my God. Several of you are screen recording. Awesome. OBS? Nice. We have some Twitch streamers in the chat, I see. Okay. Okay, good. several people were already recording. So I know that to anyone watching this currently, several of your classmates have a recording that they locally recorded of this because I accidentally forgot to. So if you just send an email out or send a text to the group text, I'm certain that someone will immediately send you a video. I apologize for not recording it myself. All right, and that was to all the future people who could be watching this. What happened was I accidentally forgot to record. However, several of your classmates have a recording because they were recording this. So it's not a big deal. Anyway, let's move on to section 1.5 here. We are now on 1.5. We have to move on to this idea of inverse functions. Before we get to this idea of inverse functions, we have to define what's called a one-to-one function. It's okay. Several people have a recording of it. Several people recorded me in OBS. Yeah, exactly. A function that is one-to-one never takes on the same value twice. The times for the Monday, Wednesday classes are also the same time. There's 6 to 7:50. They don't appear on your schedule because we are technically not scheduled for those meetings. We were planned for those meetings. Those meetings are technically not required for you to attend. However, it's strongly recommended that you attend if you do not have a conflict, as we will be covering new material in those, as it is not going to be possible for us to cover all this material if we only meet 2 days a week. So if you're not able to make it, then you will have to watch the recordings. This is the beginning of 1.5, yeah. So the idea of a one-to-one function, yeah, there was one this Monday. There's a recording in Blackboard. Yeah, no problem. The idea of a one-to-one function is that it never takes on the same value twice. And just as we discussed the vertical line test for functions, one-to-one functions have to also pass what's called the horizontal line test. The horizontal line test says a function is one-to-one if and only if no horizontal line intersects its graph more than once. One-to-one functions also have to pass the vertical line test, right? Because they have to be functions. So in order to pass, in order to be a one-to-one function, you have to pass both the vertical and the horizontal line tests. And if something is a one-to-one function, then it has an inverse. Let f be a one-to-one function with domain A and range B. Then its inverse function, which is denoted with a -1 superscript, it's denoted with an f and a -1 superscript. This has domain B and range A, and is defined by f inverse of y is equal to x if and only if f of x is equal to y for any y in B. So this is just saying that the way that we obtain an inverse function is by swapping the domain and the range of this one-to-one function. Does that make sense? This just says that the domain of f inverse is the range of f, and the range of f inverse is the domain of f. We obtain an inverse function by swapping a function's domain and range, by swapping its x and y values. I don't want to spend too much time on one-to-oneness One-to-oneness is easy to judge based on performing the horizontal line test, right? Can I move to the next thing, the properties of inverse functions? Fine by you. Yes, yes, yes. Good. Here we have two properties of the inverse functions. This one we just wrote. F inverse of x is equal to y if and only if f of y is equal to x. A bit of an implication here is, well, let's see. This says f inverse of x is equal to y, right? If f inverse of x is equal to y, then this is telling me that f inverse of, or rather, if f inverse of x is equal to y, then this is telling me that f of f inverse of x is equal to x. Right? This is just from plugging this into here. And this is what we have down here, huh? Similarly, if x is equal to f of y, then plugging f of y in for x over here, similarly undoes this equation, right? The idea here is that functions and their inverses undo one another. They unravel one another. If you compose a function and its inverse, you simply receive whatever argument is inside the innermost of those functions. Does that make sense? For now. Okay. So I just said that functions and their inverses undo one another. What this means is that if you compose a function and its inverse, that you receive, as a result, whatever the argument is inside the innermost function. In this most simple of examples, we just get x. Right? The argument of this innermost function here is x. An example of this is, let's say f of x is x cubed. Without going through the process that we're going to look at in a second, the inverse of this is x to the 1/3, which is the cube root of x, right? The cube root, we should realize that the cube root of x and x cubed undo one another, right? Well, let's compose them. F inverse of f of x is f inverse of x cubed, which is x cubed to the 1/3, which is x. F of f inverse of x is f of x to the 1/3, which is x to the 1/3 cubed, which is also x. Does this make sense? Let's look at how to find inverse functions of one-to-one functions. It looks like we may not have time to get to logarithms today, which means that we'll just pick up tomorrow with the logarithm stuff. Go back for a second. So Tomorrow, we're going to begin with the very end of 1.5. Just a heads up. We don't have quite enough time to get to the logarithm stuff today. Without just skipping over inverses completely. And that's a result of having to go through 3 sections today. So, let's never do it again. This is what we have to do, unfortunately. How to find an inverse. Write y equals f of x. So all we're doing is we're replacing f of x with y equals. Then this says solve this equation for x in terms of y. What this is really saying to do here is swap x and y and solve for x, or solve for y, rather. Swap x and y, solve for y. Or you can solve the equation for x. I like to swap x and y and solve for y because for some reason, to my brain, it feels weird to solve for x in an equation. Does that make sense? It feels weird to me. And this last step anyway involves interchanging x and y. So I'll show you the way that I prefer to find these inverse functions. For instance, let's find the inverse function of f of x equals x cubed plus 2. So let's rewrite this as y equals. Again, I prefer here to swap x and y. So this is x equals y cubed plus 2. And then subtract 2 from both sides. So this is x minus 2 equals y cubed. And in order to undo the cubing on the y, I take the cube root of both sides. So we get that y is the cube root of x minus 2. And then we replace this y with f inverse of x equals the cube root of x minus 2. Does that make sense? Yep, that's the final answer. Yeah. They want you to do this, except the way that the book does it is they don't swap the x and y, right? They instead solve for x here to get x equals the cubed root of y minus 2. And then they swap the x and y at the end. We both swap x and y. I prefer to swap mine at the beginning. They swap their x and y at the end. And then they write this as f inverse. Yeah, the interchange step here can occur at any point. Does this make sense? Does this process make sense? Looks good, same result. Yep. Let me just grab this. Regarding the graphs of these functions of inverses, the graph of f inverse of x is obtained by reflecting the graph of f about the line y equals x. That's really the only comment that needs to be made regarding the graphs of these functions. They are reflections of one another across the line y equals x. Now, what if I want you to find the inverse of f of x equals 2 to the x power? What should we do here? What should we do here to find this inverse? X to a y, use logs. Saying use logs is opening your presents early. Y equals 2 to the x. You said x equals 2 to the y. Well, he didn't leave his wife. He only returned all of her Christmas presents and didn't buy her anything new. At this step, there's not really anything that can be done with the current tools that we've discussed, right? So far in this class. Because the inverse of f of x equals 2 to the x is going to be log base 2 of x. Right? And we're going to discuss these kinds of functions beginning in our next class. We're going to talk about logarithmic functions in our next class. This is the end of 1.5. Or probably it's really about the midsection because 1.5 is a bit lengthy. We're not going to talk too much in length about the inverse trigonometric functions, although maybe we'll discuss them for a second. And then next class, we are going to discuss 2.1 and 2.2, and that's going to be tomorrow. Help? Help with what? With logarithms? Who has the recording? Okay. Yeah, not me. So contact one of your colleagues here who has the recording. One of your peers, I suppose, would be a better word. Yeah. Man. And that's after I told y'all that I was going to be recording too. Y'all don't trust me, do you? Can you ask about the homework? Yeah. What about the homework? Yeah, what about it?
Sorry, I needed to put a headphone in. The WebAssigns videos are great. They're really helpful. But the way that they solved for the difference quotient in one of my questions was really confusing.
Okay.
Darn, I wish I could like share the screen or something. Well, technically I could share a video, but I'm not about to do that right now.
Do you know which question?
Yes, it was number 2.
Number 2? Okay. Let me see what their explanation is real quick.
Okay.
Blah, blah, blah. Oh, yeah. They did this. They did this. Okay. So the way that, okay. Let me pull up the question again. Oh, wait. So I think it pops out in a separate thing. There we go. So yeah, there's a slight different form of the difference quotient there. Good eye. Is it in the textbook? Well, which slide? So the form of the difference quotient that's given in the homework, good eye, is slightly different. It's f of x minus f of a over x minus a. This is a different form of the difference quotient. And this is also important because we're going to be using this once we get into a little bit more calculus-y stuff. So all you have to do here is find f of a, and then just plug in f of x and f of a, and simplify. Does that make sense? For instance, I'm given f of x is 1 over x. Also, what do you mean by the first slide with y equals and everything?
It was like a bunch of y equals, and then you had like a graph, and then you had more like y equals.
Do you mean like this?
It was the very first slide, not that. So I guess slide after
that. This?
Yes. Is that in the textbook or no?
This is in the textbook. This is in section 1.3.
1.3.
Mm-hmm. This should be towards the, I think it should be towards the beginning of 1.3. Let me check.
Okay.
Yeah, this should be basically the first or the second page of 1.3.
Okay, thank you.
No problem. So for this here, all we have to do is find f of a, which is just replacing x with a, right? And then just plug in the stuff that I know.
Why was f of x 1 over x again?
I was given this in my problem.
Oh, okay, I see it. I'm sorry. Okay.
No problem.
Yeah, and then they multiplied top and bottom by xa or ax.
Yes, and that's to get a common denominator.
So I think I got confused in that part by the common denominator part.
Okay, so we want to get a common denominator here so that we can combine these things. Because our goal here is to try to simplify this as much as possible.
Oh.
So I have this minus x over ax, right?
Mm-hmm.
All over x minus a. At this step, I can combine them over one denominator.
Okay, I'm following.
At this step, what they did was they combined this to be, they said that since I'm dividing everything by x minus a, that's the same thing as just having x minus a in this denominator here. Since everything's being divided by x minus a, it's just the same as throwing x minus a in that first denominator.
Okay.
Does that make sense?
A little bit.
From here, they notice the similarity between a minus x and x minus a, right?
Mm-hmm.
So it looks like I might be able to manipulate this to get something to cancel. It's ax. Or no, it should just be this. No, we don't need to distribute anything here yet. What we should do is factor a -1 out of a minus x to get x minus a here. Because if we do this, then this causes these x minus a's to cancel.
How can we factor the -1 out and leave the sign as negative inside?
Okay, let me break that down. So it's because this becomes, if I factor a -1 out, then this becomes -a plus x, right?
Oh, I hate when they. Okay.
Does that make sense?
Yes, it does. Sadly.
So sometimes we just have to see it like that, right?
Mm-hmm. It always confuses me to take a negative out of a positive. Like, I'm like, huh, what?
Yeah, sometimes we just have to see things in a slightly different way.
And then that's how we just get ax?
Or
negative ax?
Because now we can carry out this division, which leaves me with just this -1 up here and an ax in my denominator.
Okay. Yeah, that was good. I liked, because, like watching the videos, I feel like they know something that I don't. And so I'm trying to do the work, freehand, and I'm like, I don't know what to do next. And their video doesn't show me what to do next. It's just like very quick. And I'm like, I don't understand what was in between.
I see.
Oh man, I think there was another one. If you have time for it, if not, that's okay. I can just email you about it.
Which one?
I think it's number 8.
Number 8. Let's see.
Determine if even, odd, or neither.
Okay, so to do that one, I won't work that one out all the way, but do you explain what needs to be done with homework and the online textbook on Monday? Do we have access to these slides? So the homework, all of the sections that we're covering this week, which are on the syllabus, it's everything through to 2.3, are all due on Saturday. They're all in WebAssign. So just complete all of those assignments before Saturday at 11:59 p.m. For number 8 here, for number 7 is the same kind of problem, right? It's even, odd, or neither. What we want to see is to check to see if something's even, odd, or neither. We have to plug -x in for x in that function. So I have to plug in -x. And if I get the original function back out of it, right, with nothing changed, this means that the function's even. If, whenever I plug -x into the function, I get the same function, but all of my signs are changed. That's what this indicates, right? It indicates I put a negative sign in front of the function, which changes all of the signs. This means that this function is odd. And if neither of these are true, it's neither. Does that make sense?
Yes. So are we just changing the sign of x when we reverse it? Or,
for instance, I have 7 plus 7x cubed minus x to the 5th. This is f of x, right? F of -x is what I get whenever I replace my x with a -x. Does that make sense?
Yes. Is that due?
Yeah, let's do them. Hold on one second.
Mm-hmm.
All right, sorry, our food was being delivered. I just needed to see if I needed to do anything. So all I did here was to find f of negative x, I just replaced x with negative x. And at this point, I just simplify everything, and I see, is it equal to the original thing? Did all of my signs change? Or are neither of these things true? Does that make sense?
Mm-hmm.
Awesome. I do have to go now, though. As my food just arrived.
Okay. I think it became neither. I'll try to figure that out. Okay. Thank you. Thank you so much.
Awesome. Have a great. And if you have any questions, feel free to email me, stop by office hours, etc. And I will get back to you as soon as I can, which should be pretty quick. Thank you. I shall. Have a great night, everyone.